Nobody knows the trouble I've seen. Nobody knows my sorrow. Nobody knows
Okay. All right.
trouble.
I'll bite. What's going on? What's this all about?
Chapter 11.
Okay. Yeah, chapter 11. It's about stoichiometry. Stoichiometry, the measuring of elements. What's the big deal?
Yeah, well, do you know how I got this way?
Actually, no, I don't. I don't know how you got it.
2014, your stoichiometry test.
Okay, all right, that's enough. Look, you're just going to scare them by talking this way, so just clam up for a moment. Look, folks, in this chapter, yes, we will talk all about stoichiometry, how we measure elements in a chemical reaction. So don't let this guy scare you. We're going to take all the fear out of stoichiometry for you and show you how to complete stoichiometry problems. So let's get started.
By the way, get a haircut, hippie.
What? If you're wondering how we got the word stoichiometry, it actually comes from two Greek words. One, stoichion, meaning elements, and metron, meaning to measure. So literally, stoichiometry is measuring elements. It's the study of the quantitative relationships between the amounts of reactants that are used in a reaction and the amounts of products that are formed. Quantitative having to do with quantity, right? The key to stoichiometry is the law of conservation of mass. Remember that in every reaction, the mass of the reactants must equal the mass of the products. So we can use that principle of the law of conservation of mass to determine how much of a reactant is being used or how much a product is being formed during a chemical reaction. That's the reason why we must balance our equations. Take a look at this equation right here. The reaction of methanol and oxygen to form carbon dioxide and water. Notice that when we balance this equation, we have coefficients in front of each of these compounds. Whenever we don't have a coefficient in front of a compound, it simply means 1. Those coefficients can actually have more than one meaning. For instance, in this equation, 2 molecules of methanol combined with 3 molecules of oxygen yield 2 molecules of carbon dioxide and 4 molecules of water. But not only that, we can also use moles. 2 moles of methanol combined with 3 moles of oxygen will give us 2 moles of carbon dioxide and 4 moles of water. So you see, it can work in more than one way. Just so you can see how this correlates with the law of conservation of mass, let's see what happens when we use actual gram amounts for each of these. The molar mass of methanol is 32.05 grams per mole. If we have 2 moles of that, that makes 64.10 grams, right? Okay. Oxygen, O2, has a molar mass of 32 grams per mole. If there's 3 moles of that, that gives us 96 grams, doesn't it? So far, so good. On the other side, the molar mass of carbon dioxide is 44.01 grams per mole. If we have 2 moles of that, that means we have 88.02 grams. Water has a molar mass of 18.02 grams. So if we have 4 moles of it, that makes 72.08, doesn't it? Now watch this. Let's add the masses of the reactants together. What do we get? Right, we get 160.1 grams. What happens if we add together the masses on the product side? Again, we get 160.1 grams. So you see, this tells us that we're in agreement with the law of conservation of mass, that the mass of the reactants and the mass of the products in a chemical reaction are always equal. So now that we've proved that to ourselves, let's talk for a moment about mole ratios. What do I mean by a mole ratio? A mole ratio is the ratio between the numbers of moles of any 2 substances in a balanced chemical equation. In our former reaction with methanol and oxygen, we know that for every 2 moles of methanol, we need 3 moles of oxygen. That's a mole ratio. That's a relationship between those 2 compounds in this reaction. So we could say 2 moles of methanol for every 3 moles of oxygen. We can do the same thing with methanol and the other compounds in this reaction. 2 moles of methanol for every 2 moles of carbon dioxide, for instance. Notice that I'm simply using the coefficients in front of each of these compounds in order to form my mole ratio. Finally, we can say 2 moles of methanol for every 4 moles of water. But that's just the methanol. We can also do this with oxygen. We can give the relationship between oxygen and the other compounds as well. 3 moles of oxygen for every 2 moles of methanol. 3 moles of oxygen for every 2 moles of carbon dioxide, and 3 moles of oxygen for every 4 moles of water. And yes, we can do that with the products as well. 2 moles of carbon dioxide for every 2 moles of methanol. 2 moles of carbon dioxide for every 3 moles of oxygen. 2 moles of carbon dioxide for every 4 moles of water. Let's show the ratios with water and the other compounds. 4 moles of water for every 2 moles of methanol. 4 moles of water for every 3 moles of oxygen, and 4 moles of water for every 2 moles of carbon dioxide. So these are all the mole ratios that we can form in this one reaction. Hopefully you see how I did that. I just took one compound and related that compound to the other compounds in the reaction. We need to be able to recognize these relationships between the compounds later on when we do our stoichiometric calculations. By the way, a quick way to know how many mole ratios you have in a particular reaction: simply count the number of substances in your reaction. In this one we have 1, 2, 3, 4 different substances. They could be elements or they could be compounds. Take that number and multiply it by the number that's one less. In this case, 4 substances times 3 means that we'll have 12 total mole ratios. In other words, to find the mole ratio, multiply n number of substances by n minus 1. Here's an assignment for you. Take this reaction, the reaction between zinc oxide and hydrochloric acid that forms zinc chloride and water, balance it, and then determine all the possible mole ratios. You can put your answers in the LMS. That's all we're doing for this video, in which we began our coverage of stoichiometry. We talked about what stoichiometry means and how it fits with the law of conservation of mass. Then we showed how we can determine mole ratios for a particular reaction, which will be useful for us later on. In our next video, we'll do some actual stoichiometric calculations and hopefully take some of the fear out of stoichiometry. So until next time, God bless.